there is this other version of Arnold conjecture involving Lagrangian intersection, right? But then maybe I won't stay, or maybe I'll stay. So Arnold conjecture. Number 2. Let me say it like that. So assume maybe I'm still going to call it M. M is a compact Lagrangian, but now it's a Lagrangian. Okay, that's a bad way to do it. Right? Should I call it L?
L.
Yes. Okay. Okay. M is a compact. L is a compact Lagrangian. Let's say for simplicity in a compact manifold, because I don't want to deal with its ends. Okay, in a compact quadratic manifold. M. And let's assume that P of L is a Hamiltonian deformation of L, right? Hamiltonian deformation. You push it with a Hamiltonian deformation of L, which is transverse to it. Right? So let me draw the picture. So here is your Lagrangian sitting in some ambient space that I feel good if it's compact, but the Lagrangian is compact. And here is a deformation of it, which intersects it transversely. Right, so I just do transverse intersections. Transverse to L. This replaces the condition that it's non-degenerate. Okay, this is equivalent to non-degenerate, because really this is what it means a non-degenerate fixed point. It means transverse intersection with a diagonal, if you think about it. So anyway, transverse intersection. Right. Then I'm going to finish. So these were the assumptions, not maybe so efficiently written on the blackboard as on that blackboard, but anyway, here they are. We have a Lagrangian, compact Lagrangian, and we have a Hamiltonian deformation of it, which intersects it transversely. Then the number of intersection points between the two is bounded below by the dimension of the homology of the Lagrangian. Okay, this is the homology of the Lagrangian which is bounded below. In particular, this means you cannot push it off itself, because hopefully this Lagrangian has some homology, if nothing else H0, because it's compact, right? So in particular, you cannot push it off itself by a Hamiltonian deformation. Okay? This requires some assumptions. Okay. But anyway, that's the conjecture, right? And again, what was the Fleur's idea? Fleur's idea was to do the very same thing, to do Hamiltonian Fleur theory. Sorry. We're doing Lagrangian intersection. So right now we're going to do Lagrangian Fleur theory. So in the theory of Lagrangian Fleur theory, you have two Lagrangians, ideally. You have two Lagrangians, L1 and L2. You could have more if you want, but let's stay there. And then the only requirement that you need to begin with is that they intersect transversely. Okay, two transverse Lagrangians. They will intersect in finitely many points, which I forgot to say that generically a Morse function, a Morse function would have isolated critical points, right? That was important, and the same thing happens here. We have generically, these guys, if they are transverse, they would have finitely many intersection points. But anyway, we're assuming it's transverse. And then we're going to do the same business. We're going to make a complex out of intersection points. And the differential for some reason that rings only when it's getting close to the end of the lecture. Did you notice that?
I did
It does it when you push the
beginning.
board up.
I did it at the beginning.
It depends when I push the board up. I see. So I use this board only towards the end. I see. Okay. I thought it somehow no. Somebody must have, hit a bell or something. Ready? It's time to wrap it up. I noticed in my previous lectures too that 5 minutes left and I hear that bell ringing. All right, so you make a complex out of the intersection, and what will the differential do? Well, it will count. Well, I have the picture upstairs. I won't bring it down anymore. Let me draw it again. Here are our two Lagrangians, L1 and L2. here is their intersection points, two of their intersection points may be x and y. And what the differential will count the number of holomorphic strips going from one to another. So here is the picture of the domain. And this is U. So differential counts number of holomorphic strips with boundary on L1 and L2 and asymptotic. Let me make S, so right now I made it horizontal. I followed your advice and I made things horizontal. So S goes that way, this is the S direction. So as S goes to an asymptotic, as S goes to infinity, well, I should have labeled them as X plus and X minus. Let me change their names and call them X plus and X minus. X minus and X plus. They're asymptotic as S goes to plus or minus infinity to X plus or minus. Okay, these are the intersection points now. Okay. So as you go this way, so it's a strip. This part of the boundary lies, let's say, on the upper, on L2, and this part lies on L1. Okay? And then it's asymptotic as you go this way to X plus, and as you come from this, it's coming from X minus. Okay? So that's the idea. And then from this, again, you make the same thing. It's really a Morse theory. There is also an action functional in the back, and it's really doing Morse theory for a certain action functional. But at the end of the day, you get, if everything works well, you get what's called Lagrangian floor theory. H bar of L1, L2. And I just want to say it comes out the same way from looking at the moduli space of holomorphic strips, just the same way as before. The only problem is, right now, if you look at the moduli space of holomorphic strips, you still have a notion of energy, and I'm not going to bother you with. You still have a notion of, they will still be asymptotic to the intersection points. You still have to compactify it, and the compactification will involve broken strips and bubbles, and so on and so forth. And so the moduli space will still be a manifold. So you are still hoping that you get something of that sort, where the moduli space is generically a smooth, compact-oriented manifold with boundary and corners. That's the only thing you are giving up when you do Lagrangian floor theory, unless you put some extra topological assumptions. Oriented will also go. I mean, as you see, as we're moving down the line, we're sort of dropping more and more of the adjectives, and somehow we're still trying to get to some topological consequences, but that means it's going to be harder and harder to get something out of it. But anyway, under some topological consequences, it's still oriented, so you can still do something with it. But the problem with it develops yet one more problem. So maybe say it like that. So this one has two extra problems, if you want to call them that. Although you may think that this is a good thing, right? As I said, you may take it into your advantage. But from my perspective, this moduli space has two extra problems. Besides being a manifold with boundaries and corners, which by now we're happy with, the other two problems, extra problems that it has, it may not be orientable. Okay, so then you need some topological, you need to do something about that. Let me just leave it like that. You either impose topological conditions or you figure out another way to extract invariance. And the second problem it has is actually when you try to construct this floor theory. So how should I say? Boundary square may not be 0. Okay? So then it's called, it may be obstructed. In other words, it may be obstructed. If boundary square is not 0, there is an extra term which may not die. Under some topological conditions, you can kill it. But in general, it could be there. Okay, and so anyway, so that's why it may not be. So it may be what's called obstructed. But if it's not obstructed, right? So if the obstruction vanishes, if the obstruction vanishes, and there are various versions of how this obstruction looks like, so I'm not going to, if you want more details, you can read in Fukaya Otto Ono's book. they talk about the bounding chain and whatever, deformation to the, how do they call it, to the bulk or something. So I can explain all that, what it means sort of from the perspective of what I was talking here. But anyway, it may be obstructed, but if obstruction is 0, and also you deal with orientation, and for example, the Lagrangians are spin, one of the conditions that will assure orientation is to make them spin, have a spin structure.
Sorry,
Yes.
orientation of what?
Of the moduli space of
Moduli
solutions.
space.
Yes, it's always, it's always the hope, right? Remember our hope was generically for smooth, oriented, compact, manifold, hopefully without boundary and so on and so forth. And we had to drop a bunch of those adjectives. Well, from the beginning, the generically and the smooth had some stars on them anyway, right? So, and slowly we're dropping everything except for compact, okay? Maybe that's the only one still there, surviving. If we drop that one, I don't know. Maybe one day it will be dropping that one. We'll figure out what to do with it. But let me just say, so if this is 0 and for example is spin, then you could get something, and you can get, so what happens is the very same situation, maybe I'm already way out of time. But what you can do in this situation to prove Floor's conjecture, this was not a very good use of blackboards, right? Yes. Oh, but here, wait. Yes, exactly. This was not too bad. Not as bad as I thought, right? Yes, okay, yeah.
So if the square is not square, does that mean our Lagrangian homology is not well defined?
Yes, Lagrangian homology sometimes is not well defined.
So we need some equations.
We need something else. There are various tricks you can do, but in many cases it's well defined. For example, if you do Hagar-Floor theory, it's really a Lagrangian intersection between two Lagrangians, and that one is well defined. If you want, it's good enough that it is well defined, and you can use it to get Hagar-Floor homology. Okay, so, but if you want to do it in complete generality, well, maybe you needed some extra IAS. But so far, it seems to be obstructed and not well defined in complete generality. But with some extra topological assumption, it becomes well defined.
So it's as well then. No.
Well, depends. It applies to more general cases. It applies not just to graphs, right? So here, I brought the conjecture. The way this conjecture works is the two Lagrangians you are using is a Lagrangian, it's a Hamiltonian perturbation of it. Right? This theory works for any two Lagrangians as long as it intersect transversely. You may not be able to, it may not be well defined. You may not be able to calculate it, and so on. But anyway, it works in general, right? And for example, if you knew it was non-zero, it told you the Lagrangians had to intersect, right? And it should be an invariant also. I forgot to say that. At the end of the day, you also want to get an invariant, and say up to Hamiltonian deformation of the situation.
So this floor homology is helpful for
Yes. So this is the last thing I want to say. I'm already out of time, but the way you would use this for the Arnold conjecture is you would do the floor homology of the Lagrangian and psi of the Lagrangian. This is a Hamiltonian perturbation of it, okay? And in this case,
Now you start slurring chalk.
right, so let's not talk in the audience. I've had, and what you would do, you would actually prove that in this case it's unobstructed. In other words, all these things are actually not there, and well defined and independent of choices. And it can be calculated. And when you calculate it, it's exactly the homology of the Hamiltonian. Okay? That's all. Of the Lagrangian. Yeah. So here one is well defined just as you hoped, is well defined, independent of choices, and can be calculated for small Hamiltonian perturbation, because really it's the same, sort of for small. Right? And is equal to the homology of the Lagrangian. Okay? And so that's how you get Arnold's conjecture. This way, in the same way. So I'll stop here. But anyway, I just wanted to say, in my mind, all this, in my mind, the main object of the main magical tool is the moduli space of holomorphic curves and its structure. And then from it, you can show that it has certain kinds of properties, and from it you can extract invariant, and then with this invariant you can get the logical consequences. Okay, for example, existence of periodic orbits, existence of a Lagrangian intersection, the existence of curves I gave you in the first couple of lectures. All those follow from the study of sort of this moduli space of solutions, this very natural geometric equation, which is the holomorphic map equation. Okay, so I'll stop here.